The universe grew from an unimaginably small size to something vast. If a quantum fluctuation triggered this expansion, it would mean that the universe itself emerged from the hidden energy of empty space.
If one quantum fluctuation could create a universe, could others do the same? Some scientists believe fluctuations like this might happen all the time, producing countless universes beyond our own. This idea, known as eternal inflation, suggests that new regions of space are constantly forming in an ever-expanding cosmic landscape.
Even within our own universe, quantum fluctuations left their mark. As inflation stretched space, tiny fluctuations were magnified. These small differences in energy density became the seeds of galaxies and stars. Without them, matter might have remained evenly spread, never clumping into the cosmic structures we see today.
The idea that the universe could emerge from nothing may seem strange, but experiments confirm that quantum fluctuations are real and have measurable effects. In particle physics, they influence the behavior, fundamental forces, and particles. If they shaped the universe on the smallest scale, they may have influenced it on the largest scale too.
Vacuum energy isn't just a backdrop. It can shift from one state to another. In some theories, if an unstable vacuum state existed before the Big Bang, a quantum fluctuation could have triggered a transition, leading to the birth of the cosmos. If a quantum event started our universe, could other universes be forming right now? Could new universes emerge in the distant future? These possibilities arise naturally from the strange rules of quantum physics.
The Big Bang is the foundation of modern cosmology, the event that marks the start of the observable universe. But what if it wasn't the true beginning? For decades, physicists and cosmologists have explored the idea that the universe had a history before the Big Bang.
Some theories suggest that the cosmos has gone through endless cycles of expansion and contraction, never truly beginning or ending. Others propose that our universe was born from a much larger pre-existing reality, possibly through interactions between hidden dimensions or unknown physical forces. If these ideas are correct, the Big Bang was not the beginning, but just one event in a much older and larger cosmic story. One of the most discussed alternatives is the cyclic universe model. This theory suggests that the universe follows a repeating pattern, expanding, slowing down, contracting, and starting over again, instead of a single Big Bang followed by endless expansion. The cosmos could go through an infinite series of Big Bangs and Big Crunches. Ancient cultures, including Hindu and Buddhist traditions, imagined the universe as undergoing endless cycles of creation and destruction. In modern physics, this concept has been explored in various forms. Some versions propose that dark energy might one day reverse, pulling everything back together. The universe would shrink down to an incredibly dense state before bouncing back in another explosion. This process, repeated infinitely, could mean that the universe has no true beginning or end, only endless rebirth. A variation of this idea is the Big Bounce theory. It suggests that rather than collapsing into a singularity, a previous universe reached a highly compressed state and then rebounded, creating our current expanding universe. In classical physics, gravity would eventually pull everything back into a single point, creating a singularity. But in quantum mechanics, effects at the smallest scales could prevent this total collapse. Instead of a singularity, a new expansion could begin, leading to a fresh universe. Some versions of this theory suggest that each new universe might carry imprints from the previous one, tiny differences that could be reflected in the cosmic microwave background. String theory proposes that the fundamental building blocks of reality are tiny vibrating strings, rather than point-like particles. In one version of string theory, called the ekpriotic model,
The universe was formed not by a singular explosion, but by a collision between two enormous, higher dimensional surfaces known as branes. According to this idea, space could have more than the three dimensions we experience, and these higher dimensional structures could interact in ways that create entire universes. In that case, the Big Bang would not be a unique event. It would be just one of many such collisions occurring across an unimaginably vast cosmic landscape. Another possibility is that the universe emerged from quantum fluctuations in an eternal vacuum. If a fluctuation occurred under the right conditions, it could have triggered rapid inflation, leading to the birth of our universe. This idea suggests that our universe is just one bubble in a much larger quantum reality, constantly giving rise to new universes. This leads to the idea of the multiverse, a vast collection of universes, each with its own unique properties. Some versions of the multiverse theory propose that every quantum event spawns a new universe, creating an endless number of parallel realities. Others suggest that different regions of space are constantly producing new universes, separated from one another by immense distances, or even by different dimensions. If true, this would mean our universe is just one of countless others, each with its own physical laws, matter, and possibilities. Some theories suggest that instead of starting at a single moment, time could stretch infinitely into the past. In this view, what we see as the Big Bang might simply be a transition from one phase of existence to another. One way to explore these ideas is through mathematical models and observations of the cosmic microwave background radiation, or CMB. This faint glow left over from the early universe carries clues about what happened in the first moments after the Big Bang. Some scientists believe that subtle patterns in this radiation could reveal hints about a pre-existing universe. If traces of an earlier phase of the cosmos were found, it would be a major breakthrough in our understanding of cosmic history. Since the laws of physics, as we know them, break down under the extreme conditions of the early universe, it is difficult to gather direct evidence about anything that might have come before. Many of these ideas, while based on solid theoretical foundations, remain speculative because they cannot yet be tested. However, advances in physics and technology may one day provide new insights. As scientists develop more precise instruments and explore deeper questions about the nature of space, time, and matter, they may uncover clues that point to a time before the Big Bang. Quantum gravity plays a central role in the question of cosmic genesis. The universe follows two sets of rules that seem completely different. One set governs how planets, stars, and galaxies behave, following the familiar laws of gravity first described by Isaac Newton and later expanded by Albert Einstein. The other set governs the strange world of the very small atoms, particles, and the energy fields that surround them, described by quantum mechanics. Both theories have been tested and confirmed in countless experiments, yet they seem impossible to combine. This is a major problem, because to truly understand the birth of the universe, both gravity and quantum mechanics must be considered together. At the moment of the Big Bang, the entire universe was packed into an unimaginably small space. This means gravity was acting at the quantum scale, where the rules of quantum mechanics take over. But Einstein's theory of general relativity, which explains gravity on large scales, does not work at the quantum level. Similarly, quantum mechanics, which describes small-scale physics, does not include gravity. The two theories break down when combined, leaving physicists without a complete explanation for the earliest moments of the universe. To understand cosmic origins, scientists must develop a theory that merges these two fundamental forces into one unified framework. One approach to solving this mystery is the search for quantum gravity, a theory that explains how gravity works in the quantum world. This is considered one of the biggest unsolved problems in physics. If a theory of quantum gravity is found, it could reveal what happened in the first instant of the universe, possibly even before the Big Bang itself.
One of the leading ideas in quantum gravity is string theory. Instead of treating particles as single points, string theory suggests that everything is made up of tiny vibrating strings. These strings are so small they would be impossible to see even with the most powerful microscope. Depending on how they vibrate, their strings could represent different forces and particles, including gravity. In this view, gravity is not a separate force, but an effect of these vibrating strings interacting with space. String theory also suggests that space may have more than 3 dimensions. While we experience height, width, and depth in our everyday world, extra dimensions could exist hidden from view. If true, the early universe may have behaved very differently than we expect. These extra dimensions could have influenced how space expanded after the Big Bang, or even played a role in how the universe came into existence in the first place.
A different approach to quantum gravity is loop quantum gravity. Instead of treating space as a smooth background, this theory suggests that space itself is made of tiny, indivisible units. Much like pixels on a screen, these quantized bits of space create a structure that could prevent the universe from collapsing into a singularity. This could explain how the universe transitioned from a previous state into the one we see today. Some versions of loop quantum gravity suggests that time itself might be fundamentally different at the quantum level. Rather than flowing smoothly, time may emerge from deeper interactions within the fabric of space. This could mean that time existed before the Big Bang, allowing for a history that stretches back beyond the beginning we currently recognize.
A third idea comes from the holographic principle. This concept suggests that the entire universe may be like a 3-dimensional projection of information stored on a distant, lower-dimensional surface. In this view, the universe's deepest structure is not made of physical matter, but of information itself. If the holographic principle is correct, the birth of the universe might not have been a traditional explosion, but rather the emergence of information forming space and time.
One of the biggest challenges in developing a theory of quantum gravity is testing it. Unlike other areas of physics where experiments can be done in labs or with telescopes, the conditions needed to study quantum gravity directly would require recreating the extreme environment of the early universe. Since that's impossible with current technology, physicists must look for indirect clues, subtle patterns in the CMB, the behavior of black holes, or strange effects in high-energy particle experiments.
Black holes are similar in some ways to the conditions of the early universe. Stephen Hawking famously predicted that black holes slowly lose energy over time through a process now called Hawking radiation. This happens because quantum effects near the black hole's edge cause particles to pop into existence and escape. If quantum gravity plays a role in black holes, studying their evaporation could provide insights into the universe's first moments. The CMB holds information about the early universe, and small irregularities in it could reveal whether quantum gravity had an effect during the first fractions of a second. If patterns appear that don't fit with standard cosmology, they could point to new physics beyond Einstein's equations.
There is also the question of whether the universe needed a beginning at all. Some theories of quantum gravity suggest that time itself may behave differently under extreme conditions. If time and space emerge from quantum interactions, then the Big Bang might not have been a singular event, but rather a transition from one state to another. The universe may have always existed in some form, with no absolute beginning, only changes in its structure over time.
If scientists succeed in merging quantum mechanics and gravity into a single framework, it could lead to entirely new ways of thinking about space, time, and the universe's structure. It might even provide the foundation for new technologies or discoveries. Scientists push forward, driven by the need to understand the fundamental nature of everything that exists.
Emergence of spacetime. When geometry is born,
Before the birth of the universe as we know it, there may have been no space and no time, at least not in the way we understand these things. The fabric of reality itself might not be fundamental. Instead, it may have emerged from deeper processes that have nothing to do with the familiar ideas of space stretching infinitely or time flowing smoothly. One way to think about this is to compare space-time to temperature. Temperature feels like a basic property of the world, but in reality it is just the collective motion of microscopic particles.
Equally intriguing is the question of what existed before the Big Bang. This is a tricky area, as the very concepts of before and time become meaningless at the beginning of our universe. According to the general theory of relativity, time and space are intertwined and began with the Big Bang. Thus, to ask what was before the Big Bang challenges the very nature of our understanding of time and causality. Some theoretical physicists, including Stephen Hawking, have suggested that speculating about what happened before the Big Bang is akin to asking what is north of the North Pole. Such questions may not make sense in our current understanding of time and space. However, this has not stopped theorists from exploring models like the idea of a cyclic universe, where each Big Bang is the result of the collapse of a previous universe, or theories of an eternal inflationary universe, constantly expanding and spawning various parts that balloon into full-fledged universes. As we continue to probe these fundamental questions with advanced telescopes and theoretical models, our understanding of the very fabric of reality could be significantly altered, potentially unveiling a cosmos far stranger and more mysterious than we currently comprehend. Building upon our understanding of the cosmos's beginnings with the Big Bang, let's explore the formation of the first galaxies in the early universe, a process that sheds light on the structures we see scattered across the sky today. After the Big Bang, the universe was initially a hot, dense plasma of particles like protons, neutrons, and electrons. As the universe expanded, it cooled sufficiently to allow these particles to combine and form hydrogen atoms, the simplest and most abundant element in the universe. This era, known as recombination, occurred around 380,000 years after the Big Bang. The cooling continued, and with less energy available, particles began to slow down and gravitate toward each other due to the force of gravity. This gravitational attraction led to slight irregularities in the distribution of matter. These irregularities, or tiny fluctuations, were critical because they acted as the seeds for the later structure of the universe. Over millions of years, these small fluctuations grew larger due to the gravitational pull of dark matter, an invisible substance that makes up about 85% of the matter in the universe, but does not emit light or energy. Scientists believe dark matter played a crucial role in galaxy formation by clustering first and pulling in surrounding gas and dust. As these regions of dark matter grew denser, they pulled in more gas and dust, forming the first stars and eventually galaxies. The first galaxies were likely small and lacked the defined spiral or elliptical shapes seen in later galaxies. They contained young hot stars that burned brightly, emitting intense radiation. This period, known as the era of cosmic dawn, was when the universe became lit up again after the dark ages that followed recombination. As more stars formed and died, they expelled heavy elements into space, which then became the building blocks for new stars and planetary systems. Over billions of years, these early galaxies merged and interacted, forming larger, more structured galaxies like the Milky Way. Understanding how these first galaxies formed helps astronomers learn more about the universe's evolution and its large-scale structure. This ongoing research is crucial, as it provides insights not only into the past, but also into the future trajectory of our universe. As we delve deeper into the mysteries of the cosmos, particularly following the formation of early galaxies, a crucial component that emerges is dark matter. This elusive substance doesn't emit, absorb, or reflect light, making it incredibly difficult to observe directly with telescope. Despite being invisible, dark matter is fundamental in understanding the universe because it exerts gravitational forces,
influencing the motion of galaxies and their clusters. The concept of dark matter first arose from the observations of galaxies that didn't behave as expected under the laws of gravity, based solely on visible matter. Astronomers, including Fritz Zwicky in the 1930s and Vera Rubin in the 1970s, noted that the stars at the edges of galaxies were moving much faster than they should be if only the visible matter were exerting gravity. These findings suggested the presence of some additional mass, hence named dark matter for its invisibility. Detecting dark matter is a formidable challenge because it does not interact with electromagnetic forces, which means it doesn't absorb, emit, or reflect light, and it doesn't interact with charged particles. Its detection thus relies on indirect methods, primarily through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Various experiments are underway to detect dark matter particles directly, such as those using specially designed detectors buried deep underground or submerged in water or ice to shield them from cosmic rays and other background noise. One popular candidate for dark matter is weakly interacting massive particles, WIMPs. These hypothetical particles would not interact with light but could exert force through gravity and weak nuclear interaction. Despite extensive searches, WIMPs have yet to be detected, leading some scientists to consider other possibilities like axions or even more exotic forms of matter. The search for dark matter is one of the most exciting areas in modern astrophysics, offering the potential to unravel one of the most significant mysteries of the universe. As technology and theoretical models improve, the hopes of identifying dark matter continue to grow, promising to enhance our understanding of the very fabric of the cosmos. Following the exploration of dark matter and its gravitational influences, another profound cosmic phenomenon is dark energy, a mysterious force that is accelerating the expansion of the universe. Discovered in the late 1990s through observation of distant supernovae, dark energy poses one of the biggest questions in modern cosmology. Why is the universe not only expanding but doing so at an increasing rate? Dark energy is thought to constitute about 68% of the total energy in the observable universe. Its effects are quite the opposite of gravity. While gravity pulls objects together, dark energy seems to push them apart. This repulsive force is uniform, spread throughout space, and increases the distance between clusters of galaxies, affecting the large-scale structure of the universe. The exact nature of dark energy is still a subject of intense research and speculation. One leading theory suggests that dark energy is a property of space itself. Albert Einstein's theory of general relativity introduced the concept of the cosmological constant, a term he added to his equation to allow for a static universe. After the discovery of the universe's expansion, Einstein called it his biggest blunder, but today the cosmological constant is seen as a potential explanation for dark energy, representing an energy density that fills space uniformly. Alternatively, some theories propose that dark energy could be dynamic, changing over time, possibly related to new kinds of fields or particles that have yet to be discovered. These ideas often extend the standard model of particle physics, leading to a rich array of theoretical possibilities, including quintessence, a field that would be less dense as the universe expands. Understanding how dark energy influences the expansion of the universe not only has implications for the fate of the cosmos, but also for the fundamental laws of physics. As the universe expands at an accelerated pace, driven by dark energy, it challenges our understanding of how forces interact on a cosmic scale. The race to unravel the mystery of dark energy involves a combination of observational astronomy, theoretical physics, and advanced simulations to predict how this expansion could continue into the future. As technology advances and observations become more precise, the hope is to gain a clearer picture of how dark energy shapes our universe, and potentially uncover new physics that could revolutionize our understanding of reality. Building on our understanding of how dark energy influences the universe, a natural question arises: are the laws of physics consistent across the entire universe? This question is fundamental to cosmology and the study of physical laws because it underpins assumptions that scientists use to understand everything from the behavior of galaxies to the formation of elements. The concept that the laws of physics are the same everywhere and at all times in the universe is known as the cosmological principle. This principle has been supported by a wide range of observations, including the uniformity of the cosmic microwave background radiation, which suggests that the same physical laws applied during the formation of these photons about 3. However, verifying the consistency of physical laws across the entire universe is challenging. The universe is vast, and our observational capabilities are limited to the light or other forms of radiation that reach us. We rely on this information to test our theories and the universality of physical laws. For instance, we observe light from distant galaxies to confirm that electromagnetism works the same way billions of light years away as it does here on Earth. There have been some intriguing findings suggesting slight variations in the strength of the electromagnetic force in different parts of the universe. These studies involve measuring the fine structure constant, which controls the strength of electromagnetism, and comparing its value in various distant galaxies. Some researchers have found hints that this constant might vary in different parts of the cosmos, but these results are not definitive and are subject to ongoing debate and further investigation. Astrophysicists also explore the consistency of general relativity, GRR, across the universe by observing the movements of galaxies and the behavior of light as it passes near massive objects, a phenomenon known as gravitational lensing. These observations have so far supported the theory of general relativity, which predicts how gravity works both near and far from us. The question of whether physical laws are consistent throughout the universe remains open and profoundly important. If future observations confirm that these laws vary in different regions of the cosmos, it would have profound implications for our understanding of the universe and the underlying principles of physics. It could lead to new theories that might explain these variations, potentially revealing deeper truths about the nature of reality. Following the examination of whether the laws of physics are consistent throughout the universe, an equally fascinating aspect of cosmic evolution is the formation of stars within the earliest galaxies. The processes that led to star formation in these galaxies are crucial for understanding not only the life cycle of stars, but also the evolution of galaxies over billions of years. In the aftermath of the Big Bang, the universe was primarily composed of hydrogen and helium. These gases filled the cosmos as a uniform fog until gravity began to pull denser regions of gas together. These regions, enriched over time by slight fluctuations in density, possibly enhanced by dark matter's gravitational effects, began to collapse under their own gravity. This is where the process of star formation began. As these gas clouds or nebulae continued to collapse, they broke into smaller fragments. Within each fragment, the gravitational force caused the gas to compress further, heating up as it did so. When the core of a collapsing cloud reached a sufficiently high temperature and pressure, nuclear fusion ignited. This fusion of hydrogen atoms into helium releases immense energy, marking the birth of a new star. The earlier stars, often referred to as population 3 stars, were likely massive and lived short but spectacular lives. Composed almost entirely of hydrogen and helium, they lacked the heavier elements present in later generations of stars. These massive stars were crucial for the chemical enrichment of their galaxies, as they ended their lives in explosive supernovae, expelling heavier elements like carbon, oxygen, and iron. These elements then became part of the gas clouds that would form the next generation of stars. The cycle of star birth, life, and death in these early galaxies set the stage for the complex structures we observe in the universe today. The remnants of these first stars seeded the cosmos with the necessary elements for building more complex star systems, possibly even those capable of supporting life. This ongoing cycle of star formation and destruction, driven by gravitational forces and the nuclear fusion within stars, continues to shape galaxies, providing a dynamic and ever-evolving universe. Following the discussion of star formation and the evolution of early galaxies, another captivating subject in astrophysics is the mystery surrounding ultra-high-energy cosmic rays. These are among the most energetic particles ever observed, with energies millions of times greater than particles accelerated in human-made colliders. Identifying the sources of these cosmic rays is a significant challenge due to their extreme energy and rarity. Ultra-high-energy cosmic rays, moving from the high-energy cosmos to the enigmatic centers of galaxies, we encounter supermassive black holes, colossal entities whose growth mechanisms are as fascinating as they are Supermassive black holes reside at the centers of most large galaxies, including our own Milky Way, and they can have masses that are millions to billions of times that of the Sun. The growth of these supermassive black holes is primarily driven by the accretion of mass. Materials such as gas, dust, and even entire stars can fall into the gravitational pull of a black hole.
As this material gets closer, it accelerates and heats up, forming an accretion disk around the black hole. This disk of swirling material moves faster as it spirals inward, heating to incredibly high temperatures and emitting large amounts of electromagnetic radiation, particularly X-ray. This radiation is one of the primary ways astronomers detect and study distant supermassive black holes.
Another mechanism contributing to the growth of supermassive black holes is the merging of galaxies. When galaxies collide and merge, a common event in the universe's history, their central black holes can eventually spiral toward each other and merge. This process not only forms a larger black hole, but also releases significant amounts of energy in the form of gravitational waves, ripples in the fabric of space-time predicted by Einstein's theory of general relativity, and first observed directly by scientists in supermassive black holes might also grow by capturing and stripping apart rogue stars that come too close. These tidal disruption events provide a feast for black holes and a brief but intense flare in brightness, offering astronomers another method to observe and study the growth dynamics of these mysterious objects. The rate of growth of a supermassive black hole is also influenced by the environment of its host galaxy. For instance, in a galaxy with abundant interstellar gas, a black hole may grow quickly by accreting large amounts of this gas. Conversely, in older galaxies where much of the gas has already formed stars or been ejected, black holes may grow more slowly. Understanding these growth mechanisms is crucial not only for learning about the black holes themselves, but also for understanding galaxy evolution. The interplay between supermassive black holes and their host galaxies suggests a symbiotic relationship, where the growth of one can influence the development and characteristics of the other. This complex dance between black holes and galaxies is a key topic in modern astrophysics, illuminating the past, present, and future of the universe. Exploring further the intriguing dynamics between supermassive black holes and their host galaxies, we find that black holes exert significant influence on their surrounding environment. These cosmic behemoths, often lying at the very centers of galaxies, play a pivotal role in shaping the galaxies they inhabit. One of the primary ways black holes influence their galaxies is through what astronomers call feedback mechanism. When black holes accrete material from their surroundings, not all of this matter ends up swallowed by the black hole. Some of it is ejected back into the galaxy at high speeds in the form of powerful jets and wind. These outflows can carry away a substantial amount of gas, the fuel for star formation, from the galaxy's core to its outer edges, or even into intergalactic space. This process can slow down or even halt the formation of new stars in the galaxy, affecting the galaxy's evolutionary path. This feedback from supermassive black holes is crucial in regulating the growth of their galaxies. For example, in more massive galaxies, the central black hole is typically larger and its outflows are more energetic. These energetic outflows can clear out the central regions of the galaxy of gas, leading to a slowdown in star formation, which astronomers observe as a correlation between the masses of black holes and the properties of their host galaxies bulging. This regulatory mechanism helps to maintain a balance in the galaxy, preventing it from becoming too star-rich, which could lead to rapid depletion of its interstellar medium. Moreover, the gravitational influence of a supermassive black hole also plays a role. The immense gravitational pull of the black hole can organize and sometimes even stabilize the orbits of stars in the galactic center. This gravitational organization can influence the dynamics and structure of the central regions of galaxies, contributing to the overall stability and shape of the galaxy. In addition to these internal effects, the presence of a supermassive black hole can also have broader implications. The gravitational effects of black holes can affect the orbits of galaxies in galaxy clusters. Additionally, the energy released by black holes as radiation can heat up the surrounding intergalactic medium, influencing the way in which galaxies and galaxy clusters grow and evolve. Thus, supermassive black holes are not just exotic objects at the centers of galaxies, but are active participants in the life cycles of galaxies. They affect everything from the formation of stars to the structure and ultimate fate of the galaxies they inhabit. This complex interrelationship highlights the dynamic and interconnected nature of celestial objects and forces in the universe, illustrating how deeply the cosmos is woven with interactions that impact scales from the local to the cosmic. Continuing the exploration of cosmic phenomena and their profound effects on our understanding of the universe, we shift our focus to quasars, some of the brightest and most energetic objects in the cosmos. Quasars provide critical insights into the early universe, shedding light on the formation and growth of the first galaxies and supermassive black holes. Quasars are a type of active galactic nucleus, highly luminous objects powered by black holes at the centers of galaxies. As material falls into these black holes, it heats up and emits an extraordinary amount of radiation, which can outshine the entire galaxy that hosts the quasar. Because they are so luminous, quasars can be observed at great distances, making them essential tools for studying the distant early universe. One of the key contributions of quasar studies is the understanding of black hole growth in the early stages of the universe. By observing the light from quasars that has traveled for billions of years, astronomers can look back in time and see these objects as they were when the universe was much younger. This provides a direct glimpse into the era when the first massive black holes were forming and growing. These observations help scientists determine the rate at which these black holes accrue mass and how they influence their host galaxies during the formative years of the universe. Furthermore, the light from quasars travels through the intergalactic medium, the space between galaxies, before reaching us. As it does so, it interacts with and can be partially absorbed by the gas and dust it encounters. Spectroscopic studies of quasars allow astronomers to study this absorption and learn about the distribution, temperature and composition of the intergalactic medium over time. This in turn provides clues about how matter was distributed across the universe, how galaxies formed from these initial clumps of matter, and how they evolved over cosmic time. Additionally, quasars can serve as probes for understanding the expansion of the universe. The redshift of the light from quasars, the way their light is stretched to longer, redder wavelengths as the universe expands, can be measured very precisely. This measurement helps astronomers refine their models of how fast the universe has been expanding since the Big Bang, contributing to broader cosmological theories, including those related to dark energy and the overall fate of the cosmos. In essence, the study of quasars opens a window into the cosmic dawn, offering a look at the processes that shaped the early universe, the evolution of galaxies, and the role of black holes in cosmic development. This fascinating class of astronomical objects continues to challenge and expand our understanding of the vast, dynamic universe. Building on our exploration of the cosmos through phenomena like quasars and their implications for the early universe, let's turn to the fundamental process of star formation and the factors that determine the characteristics of stars. Understanding how stars form provides essential insights into not only the life cycles of stars themselves, but also the broader dynamics of galaxies and the universe. Stars form within giant clouds of gas and dust, known as molecular clouds or nebulae. These clouds, mostly composed of hydrogen, are the nurseries of stars. The process begins when part of a cloud starts to collapse under its own gravitational force. Several factors can trigger this collapse, including the shock waves from nearby supernovae, the collision of different gas clouds, or gravitational effects from close encounters with other astronomical objects. As the cloud collapses, it breaks into smaller, denser fragments. Each fragment can then become a protostar, a young star in its earlier stage of formation. During this phase, the core of the protostar continues to pull in surrounding material, and as it accumulates more mass, its temperature rises. When the core temperature gets high enough, reaching about 10 million degrees Celsius, a critical threshold is met, allowing nuclear fusion to commence. At this point, hydrogen nuclei begin to combine to form helium, releasing a tremendous amount of energy in the process. This release of energy counteracts the gravitational collapse, leading to a state of equilibrium that defines a main sequence star like our Sun. The initial mass of the molecular cloud fragment determines the main characteristics of the star. The mass affects the star's temperature, luminosity, and lifespan. Generally, more massive stars are hotter, more luminous, and have shorter lifespans because they burn through their nuclear fuel more quickly. Conversely, smaller stars are cooler, less luminous, and can burn for billions of years, providing a more stable environment that might be conducive to life on orbiting planets. The composition of the molecular cloud also plays a role in defining the star's characteristics. While most of the cloud is hydrogen, the presence of other elements known as metals in astronomical terms can affect the star's evolution and the type of planets that may eventually form around it. For instance, clouds with a higher proportion of metals can lead to the formation of stars with more substantial planetary systems. Through the study of star formation, astronomers can learn not only about the stars themselves but also about the evolution of galaxies and the mechanisms that drive the development of the universe. Each star's birth and life contribute to the cosmic cycle of matter and energy, influencing the formation of new stars and planetary systems in an ongoing interstellar legacy. Continuing from the process of star formation and its implications for the cosmos, supernovae stand out as one of the most dramatic and influential events in a galaxy. A supernova is a massive explosion that occurs at the end of a star's life cycle, significantly impacting galaxy formation and evolution. Supernovae can occur in one of two main ways. The first type Wise supernova, happens in a binary star system where at least one of the stars is a white dwarf, a dense, compact stellar remnant. If the white dwarf's gravity pulls in enough material from its companion star, it can reach a critical mass and undergo a thermonuclear explosion. This explosion completely destroys the white dwarf and releases a tremendous amount of energy. The second type, known as core collapse supernova, occurs in single massive stars at the end of their life cycle. These stars, much larger than our Sun, exhaust their nuclear fuel and can no longer sustain nuclear fusion at their cores. Without the outward pressure generated by fusion to counteract gravity, the core collapses under its own weight. This collapse triggers a powerful explosion that can obliterate the outer layers of the star. The role of supernovae in galaxy formation is multifaceted. They are key to the chemical enrichment of galaxies. Supernova explosions disperse heavy elements, such as iron, carbon, and oxygen, into space. These elements, which were forged in the cores of stars or during the explosions themselves, are crucial for the formation of planets and life as we know it. The enriched material gets incorporated into future generations of stars and planets, contributing to the chemical diversity and complexity of the universe. Moreover, the shockwaves from supernovae can trigger the formation of new stars. As these shockwaves travel through a galaxy, they compress nearby molecular clouds, potentially inducing the collapse necessary to form new stars. This process can lead to bursts of star formation, particularly in regions where gas and dust are abundant. Additionally, supernovae help regulate the size of galaxies. The energy released by these explosions can heat up a galaxy's interstellar medium and drive powerful winds that blow out gas. This outflow of gas can limit the amount of material available for future star formation, influencing the growth and shape of the galaxy.
The diversity in planet types and their arrangements around their stars is influenced by numerous factors, including the star's mass and chemical composition, the disk's mass and distribution of material, and the dynamic interactions between emerging planets. These factors can lead to a wide variety of planetary systems, some with tightly packed inner planets, others with widely spaced gas giants, or even systems with planets in highly eccentric orbits. As planetary systems evolve, gravitational interactions between planets and with the debris remaining in the disk can further alter their orbits, potentially leading to stable configurations, or conversely, to dramatic events such as planetary collisions or ejections from the system. Understanding the formation and evolution of planetary systems not only provides insights into the potential habitability of these worlds, but also enriches our comprehension of how common different types of planets might be throughout the galaxy.